If you look at a map, the shortest distance between 2 points is always a straight line. So if civil engineers want to connect two cities, you would assume they would just lay down a perfectly straight highway from point A to point B. It would save asphalt, cut down travel time, and reduce fuel consumption, right? Yet if you look down from an airplane or drive across any country in the world, you will quickly notice something strange. Highways are almost never completely straight. Even on vast flat plains where there isn't a mountain or river in sight for hundreds of miles, engineers intentionally build curves, bends, and S-turns into the road. Why would road designers intentionally make your drive longer, more expensive, and more complicated? As it turns out, building a perfectly straight highway is one of the most dangerous and costly mistakes an engineer could ever make. Behind those endless bends lies a fascinating combination of human psychology, high-speed physics, geology, and economic strategy. And before we dive into the mind-blowing science behind road design, if you are new to the channel, we break down the hidden engineering, architecture, and secret mechanics behind everyday life every single week. Hit that subscribe button right now and turn on notifications so you never miss an episode. It's completely free, and it helps support the channel so we can keep making deep dive breakdowns like this one for you. Go ahead and subscribe. I'll wait. Alright, let me show you why straight roads are actually a driver's worst nightmare. The first and most critical reason roads are never built straight comes down to human psychology. Specifically, a deadly physiological phenomenon known as highway hypnosis. When a human brain is subjected to a completely straight, uniform road with zero visual changes for miles on end, something terrifying happens. The human visual system thrives on contrast, motion, and constant decision making. On a straightaway, your steering wheel remains motionless, your feet stay locked, and the scenery stays identical. Within just 15 to 20 minutes of straight driving, your brain enters a trance-like state known as automaticity. Your eyes remain open, staring straight ahead at the asphalt, but your conscious mind effectively goes to sleep. You stop registering changes in speed, you fail to notice brake lights ahead, and your reaction time plummets to near zero. In severe cases, drivers experience micro sleeps, nodding off for 3 to 4 seconds without even realizing their eyes were closed. To combat highway hypnosis, civil engineering standards in almost every country mandate strict maximum lengths for straight sections of highway. For example, federal highway guidelines in the United States and Europe generally recommend that no single straight stretch of highway should exceed 3 to 5 miles. After a few miles of straight road, engineers deliberately insert a gentle, sweeping curve, known as a transitional S-curve. This curve isn't there because of a mountain or a river. It was placed there by design, specifically to force your hands to turn the steering wheel, shift your eye focus, and re-engage your brain's active conscious network. That simple 5-degree bend in the road might literally save your life. The second reason straight roads don't exist is pure geography and civil engineering economics. From a satellite view, land looks flat and simple. But on the ground, Earth is full of microtopography: hills, valleys, rock formations, soft clay, wetlands, and underground water tables. When civil engineers design a corridor for a multi-lane highway, their primary economic goal is balancing what is known as cut and fill. If a straight path goes through a rocky hill, contractors have to blast away millions of tons of solid granite, a process that costs millions of dollars per mile. If the straight path then crosses a low, swampy valley, they have to haul in millions of tons of gravel and dirt to build up an embankment. Instead of fighting nature with brute force and astronomical budgets, engineers use sophisticated software to map out terrain contour lines. By curving the highway just a few hundred yards around the side of a hill or weaving through natural ridge passes, they drastically reduce the amount of earth that needs to be excavated. Following the natural curves of the landscape keeps construction costs manageable, preserves natural drainage basins, and prevents massive landslides. Furthermore, soil stability plays a massive role. Building a straight road over soft peat, bog, or shifting clay causes the pavement to crack, sink, and collapse within a few seasons. Curving the road onto solid bedrock or stable clay strata ensures the highway survives for decades with minimal maintenance. Now, let's talk about the physics of driving at high speeds. Have you ever wondered why racetracks have steep, banked turns? The exact same physics applies to high-speed highways, and it's another key reason roads are designed with continuous, calculated curves. When your car moves at 65 miles per hour in a straight line, it possesses immense linear momentum. If a straight road suddenly encounters an unexpected turn or obstacle, you have to apply heavy braking and turn the wheel sharply. This creates extreme lateral G-forces, breaking friction between your tires and the asphalt, which often leads to rollover accidents or loss of control. Highway engineers solve this using a concept called superelevation combined with smooth spiral transition curves. Instead of sharp turns, modern highways use parabolic clothoid curves. As you approach a curve, the road doesn't just bend horizontally. The outer edge of the pavement is gradually elevated higher than the inner edge, angling the road surface inward like a saucer. When your car enters a properly banked superelevated curve, gravity and centripetal force work together to pull your vehicle into the turn naturally. You can maintain highway speeds through the curve with minimal steering effort and zero strain on your suspension. The curve actually makes driving smoother and safer than trying to maneuver around sudden obstacles on a flat straightaway. Beyond psychology, terrain, and physics, there are legal, social, and environmental realities that force roads to curve. Highways don't exist in a vacuum. They pass through farm properties, residential neighborhoods, historical landmarks, protected national parks, and industrial zones. Under eminent domain laws, acquiring land for a highway is a massive legal and financial battle. If a farmer refuses to sell a vital tract of land, or if a straight line would cut directly through an ancient forest or a historic town square, urban planners simply route the road around the property line. Then there is an environmental factor that most drivers never think about: sun glare. If an east-west highway were built in a perfectly straight line for 50 miles, drivers traveling east during morning rush hour would be driving directly into the rising sun. The blinding glare rendered sun visors useless and caused thousands of rear-end collisions every year. The same thing happened to drivers heading west during evening sunset. By adding periodic directional curves to east-west routes, engineers shift the angle of incoming sunlight relative to the windshield, preventing long periods of direct driver blindness. Temperature expansion is another factor. Concrete and asphalt expand when heated in the summer and contract in the winter. On a 50-mile straight concrete highway, thermal expansion generates immense compressive stress along the length of the road, causing concrete slabs to buckle, crack, and pop out of the ground in severe heat waves. Curved segments allow the road structure to absorb thermal expansion laterally without catastrophic structural failure. Finally, road curvature is used as a deliberate speed management tool. When approaching major highway interchanges, toll plazas, rest areas, or transitions into dense urban cities, engineers intentionally increase the tightness of road curves. As a driver, when you feel lateral G-forces pushing against your seat during a tightening curve, your brain subconsciously registers that you are moving too fast, prompting you to naturally take your foot off the accelerator. Curving the road near high-risk conflict zones is the most effective way to slow traffic down without relying solely on speed limit signs. So the next time you are cruising down a winding highway, turning your steering wheel gently every couple of miles, remember that road was not built curved by accident. Every single bend, bank, and elevation shift was calculated by civil engineers to keep your brain awake, protect your tires, work with nature, and get you home safely. What is the most scenic or winding highway you have ever driven on? Drop your favorite road trips in the comments section below. If you enjoyed this deep dive into civil engineering secrets, hit that like button, share this video with a friend who loves driving, and subscribe for more engineering breakdowns every week. Thanks for watching, drive safely, and I'll see you in the next one.